This week we're going to look at how satellites help us monitor how things move around the ocean. And that could be ice, it could be oil, or it could be other pollutants.
As a result of its coastal location, Plymouth is home to a number of excellent marine science research institutes. I was born in this city, but I didn't know growing up that I would actually end up working at one of these, at the Plymouth Marine Laboratory, which is just to my right over here. Behind me you can also see the Citadel Hill Laboratory, which is home to the Marine Biological Association and the Sir Halaster Hardy Foundation for Ocean Sciences. And we're going to visit a number of these institutes, and we're going to learn from the remote sensing expertise that is present in these institutions in Plymouth.
So Ben, if I go to the sea and I look at it, I can see waves, I might see tides if I stay there long enough. So I can see that the ocean is moving. But I get the feeling that if we look from a satellite perspective around the globe, there might be more to this story. Can you tell me any more about how the ocean moves?
There's actually a lot more. The ocean at all scales is moving all of the time, so from the very, very tiny to the very, very large. And the very, very large scale, as a diagram of it here, is what we call the global thermohaline conveyor belt. So it's made up of two words, thermo, which means temperature, and haline, which means salinity, and you combine the two together, and what we're really looking at is the density of the ocean, so how heavy the water is. And that water, the weight of that water controls part of what drives ocean circulation around the whole planet. So what this is like a big density-driven heat engine that pumps all the water all around the planet and sends vast amounts of heat to various places, and is the reason actually why we are so much warmer than North America, being in Plymouth. So if you look at the diagram, you can see in the red lines you have what's warm water, which is usually at the surface, and in the blue lines you have cold water, which generally happens at depths and flows back along the border of the Americas out of the Atlantic. And using satellites we can actually monitor the top part of this, so the surface levels of this circulation.
An absolutely huge circulation. I mean, what sort of timescales does this circulation take? How long does it take to flow all the way around the world?
All the way around the world, anywhere from decades to thousands of years, to a millennial scale. So this is the kind of circulation that determines global climate on a basis that may be linked to when ice ages occur, or how we actually move between great climatic epochs.
Other than density, are there other things that influence the ocean circulation?
Absolutely. One of the most important things that drives circulation, especially in the surface, is the wind. So the wind constantly blowing over the surface of the ocean pushes the ocean waters in various ways, but not the ways you typically expect them to be pushed. Because the Earth is rotating all the time, the wind doesn't just push the water straight with the wind, it actually deviates off to the side, and this causes the surface of the ocean to pile up in various places, which we can detect from satellites.
So what effect does the rotation have?
So if you imagine the wind blows all the water into a big pile. If you put a ball on the top of that pile, you would normally expect it just to roll off the side of that pile in a straight line. But because the Earth is rotating, the ball, as it rolls down this hill, starts to deviate off to the left or the right, depending on which hemisphere you are in. And much the same way that ocean currents work, the energy goes to the left or to the right, and the current will actually go round the side of hills. So you can see in this next animation that what we end up with is not a load of currents that flow away from these hills, but they flow along these contours, and so you end up with patterns like the ones shown here.
So we can get information about these sorts of things from satellite. Can we pick up those hills? Can we see them using satellite data?
Absolutely. So what we can do is we can take that signal and we can decompose the surface of the ocean into a number of different modes, and one of the things we look at most regularly is the mean flow, so what the general slope of the ocean is in the background, versus the eddy flow. So this is how short-term changes driven by effectively the weather in the ocean manifests on the surface. So we can start to look at these small structures that capture very specifically given material, a biological signal or a big burst of heat, and we can use altimetry sensors as well as other satellite platforms to track those.
So there's this big global circulation that you spoke about. Are there particular parts of it that we're really interested in?
There are. You get these choke points that occur sometimes between two continents and sometimes between one large landmass and another feature, say like an ocean front, that might cause everything to get squashed up. And the Agulhas system is one of these places where this happens. So this region here between the south point of Africa and the actual frontal system, just south of it, squashes everything together and mediates how much of the warm water from the Indian Ocean flows into the Atlantic. And this is a really, really complicated place oceanographically because the current bends back on itself and spits out these eddies, and an eddy is like a large vortex of water. And in this case, they can be 400 kilometers across.
Wow, that's huge.
And it ejects these huge, great, like ping pong balls full of eddies into the South Atlantic, full of all of this heat on a sporadic basis.
And you can see that using satellite data?
You can.
In different forms of satellite data?
You can.
You mentioned altimetry, but
So
other things too?
from an altimetry perspective, we can actually look at say for an example here is the mean state in the left-hand panel, in the left-hand globe. This is kind of the background absolute height of the ocean. And then we can calculate what are the deviations from that, and that's in the right panel. And you can see at the southern point here, there are all these little lumps and bumps, all these strong red and blue parts, and those are the eddies that are coming out of this Agulhas current channel. So we can pick those up in the altimetry from the height, we can pick them up in sea surface temperature, and sometimes we can actually pick them up in ocean colour signals as well, so we can look at the biology that's contained within them. Systems like and platforms like Sentinel-3 that have sensors to look at ocean temperature, ocean colour and altimetry all at the same time in the same place are really, really valuable to look at the evolution of these various processes at the same time.
Ben, we learned earlier in the course about how the ocean transports heat around the world, but it also transports other things, like us when we're travelling in ships, for example. Can you tell me more about the other things that we can figure out how they're transported by the ocean using satellite data?
Absolutely. So we spend a lot of our time by the coast. We see things get washed away. We see things.
Yeah, I've lost a shoe in the beach before.
We see things come back onto the coast as well. And when we go in ships, obviously the ship can decide where it wants to go. However, where it wants to go most efficiently is we can often help with determining that by saying where are the currents the strongest, where are they the weakest, and we can actually use forecasting tools to do this. What we can also do is say if we drop something in the ocean, where is that then going to move to in time, or where, if we find something in the ocean, where has it come from in the past? So we can take fields of velocity data, so we can take from altimetry or from a numerical model or from a combination of the two, we can actually create a field that says if I put the thing here, it will move to here in this time, or if I find a thing here, it came from here in another time. Now those things can be harmful algal blooms, they can be oil slicks, they can be microplastics, they can be information a search and rescue might want to know about where someone who's fallen off the side of a ship might actually get swept away to. So we can actually perform experiments to find all of this information using surface current data that we derive from satellites or we derive from models.
Wow, that sounds really powerful. I mean, what sort of applications could we use that for? I mean, would that be useful for shipping or maybe for detecting things that are hazardous to us?
Absolutely. So we can use this technique to determine where our fish stocks might be in jeopardy from being contaminated.
Or where I shouldn't eat my favourite mussels, that kind of thing.
We can use it to look at oil slicks to see if we have to do some sort of environmental cleanup mechanism, where is the best place to deploy the people to do this.
Can you give me a recent example of how this has been used to help us find things that have maybe got lost in the ocean or in cases of accidents?
Well, one very recent example is on the search for the wreckage from MH370. We've actually done some studies looking at where wreckage has been found to have occurred and attempted to backtrack as to where the flight itself might have gone down.
So if I drop something in the sea, can you show me an example of how I might track where it might go?
Absolutely. So I've got an example here that I can quickly show you. In this case, we have an ocean, so we have the currents of the ocean, and we can take that either from altimetry, or so from observations, or we can take it from a numerical model, or we can do what we call data assimilation, and we can combine the two into a three-dimensional picture. And we can take that model and we can drop virtual floats, hundreds of thousands, millions, tens of millions of these floats into this model. So when I say drop a float, we just take a point and we put it in that velocity field in that model, and then we just watch where it goes in time. So as an example, here is what happens when you drop millions of floats into the coastal ocean off Japan, and you can see how they spread out across the Pacific. So these aren't real floats, these are just a representation that we can do, and we can do this forecasting in time, or we can do it at any point in where we have observations or a model for, to look at statistically where is it most likely that these points will go.